This video is going to be literally everything that you need to know about integrals. Okay, almost everything that you need to know about integrals, because I don't know if you can even talk about everything in one video. But we're going to try. So, integrals. Personally, my favorite part of calculus. They're actually really fun. So, an integral is just the area under a curve. So, if I had an integral, if I had a curve that was like this, and I want to know the area from here, here, this is A, and this is B. Then I would take the integral from A to B, and it would add up, all of this area under here for me. So that's what an integral is. And an integral is very similar to an antiderivative, where the antiderivative means the function that if you take the derivative of it, you get the original function. So generally an antiderivative is denoted with, here, let me use black, with a capital F and so you use the integral symbol, and this is like your function, and then you get your antiderivative. So antiderivative and integral are very, very similar. They're almost the same thing, but you can't exactly call them the same thing. Antiderivative is the opposite of a derivative, whereas integral is like you adding stuff up over an interval. So that's an integral. Let me make this smaller. Can go right there. This can go down here. And then I'm going to say, actually I'm going to move this down one so I can write the area under this curve is the same thing as going from A to B, from here to here, of this function, which I'm just going to call f of x. A to B of f of x dx. You always need your dx when you do integrals. So that's just the basic idea of what an integral is. So how do you solve integrals? Now, the very basic form of solving for an area under a curve is by using a Riemann sum. So what a Riemann sum is, here, Riemann, okay, I don't know if that says Riemann, but N sum. So a Riemann sum is just a way of adding up the area under a curve. So if our curve looked like this, Riemann sum uses shapes. If it doesn't specify what shape, then it's usually a rectangle. But you can have a trapezoidal Riemann sum, which uses trapezoids. And let's say we're going from here to here. So essentially what we use is rectangles. So from here to here, and the size of these rectangles depends on your what size you want them to be, how many intervals you have. So that's what a Riemann sum is. It's just adding up the area under a curve using rectangles. So this is just a rough approximation. Although this graph doesn't show it very well, but you can see there's some space under here that is not covered by this Riemann sum. See here. There's some space there. So this is just a rough approximation. I should have probably drawn a better graph, huh? Let me do that so you can see it better. Let me just erase this whole thing. Okay, we want a curvier graph. There we go. A to B. And these are our rectangles. Wait, I drew this one wrong. So the other thing about these rectangles is that the height depends on which side you're taking this Riemann sum from. So you can either have a right Riemann sum or a left Riemann sum. Now the difference is which y value you use, because the distances between for all these intervals are the same, but the heights differ. So you can have a height here to this y value, or you see this edge of the rectangle, you could have a height on this y value. So which y value you use depends on whether it's a right or left Riemann sum. So if we use left, that means we use the height of the left value, the left interval value. So if this was A and this was C, the left side would be A. So we would use the height where A is, which is this y value. And if this were like a different A, and I'm just going to call this C and D, and we're using the left one, that means we use the height where C is, which is this y value. Now if we were to do a right hand Riemann sum, we would use the right hand value, which is where this y value is. So you see the difference is what you're estimating. So if you use the right hand like here, then the rectangle would extend up here, and then you have this extra space that you're accounting for that is not under the curve. So that's why it just changes what kind of approximation you have. So when you have a Riemann sum and the function is increasing like this, then the left-hand Riemann sum will give you an underestimate. See how all of these are missing from our estimate? So that is an underestimate. But if you're using a left-hand sum and then the function is decreasing, like over here, you're going to have an overestimate, because this is all space that we're accounting for that is not actually part of the area under the curve. And then the opposite is true if you have a right-hand Riemann sum. So if we had a right-hand sum, then we would use these heights. And if it's increasing, then the right-hand sum would overestimate the area under the curve by adding up all these extra areas. And then for the right-hand sum, if you're decreasing, you would be using like this rectangle. So you're missing all this space. So a right-hand sum on a decreasing function will be an underestimate. So if that's all like hard to remember, it's okay. You can just draw out a squiggly curve and then draw some rectangles touching either the left side, with the left side of the rectangle touching the graph, or either the right side of the rectangle touching the graph, like that. And then you can imagine, okay, so this is increasing and these are right-hand sums and it's overestimate, or like over here it's decreasing and these are right-hand sums and it's underestimating. So just a quick little visualization. Now the question is, how do you actually solve for Riemann sums? So Riemann sum is notated by the summation notation, or the sigma. So what you have on the top is an n, and then on the bottom you have i's, I equaling 1. So this I is your interval. So I'm pretty sure at least, oops. Interval. Yeah, you can just say it stands for interval. So it just tells you what you're starting from. It's basically like your interval. Actually, maybe you shouldn't think of it as an interval, but that's just what number you're starting from. And then your n is how many you count to. And then you have some function here. Okay, so this is the number that's what number you're counting to, starting from 1. So that's what that means. And for Riemann sum, you see how these are all rectangles. So that means this is, so what we're doing here is adding up all the areas of these individual rectangles. So we're adding this one to this one to this one, and we're adding all of these up. And then that's our approximation of the area under here. So that means we need to add up this area, and this is a rectangle. So the area of a rectangle is this x value, which is the length, times this y value, which is the height. I probably shouldn't have colored it in, huh? Well, that's fine. I'm going to use this here. X value, y value. Okay. And I can erase this. Okay. So how do we find the x value? Well, that's going to be the change in the x's. So going from, let's call this x1 to x2, the distance between there is x2 minus x1. That's how we know what the length is. So that's why we were going to write delta x, because the delta means the change in x. And then we do the little sub I because that tells us we're taking the change in x for all of the i's. All the i's. So like just every time we add a new rectangle, essentially. And then we also have the height. So the height is the change in y values. Or no, the height is just the y value, because the height is going to be whichever side Riemann sum you pick, either this side or this side. So in our case, we're using a left-hand Riemann sum because all the left sides of the rectangles are touching the graph. So that means we're going to use, so that means all you're doing is plugging in a your x value here, sub I. So this is your y value, so, or your height, and then this is your length. So length times height gives you the rectangle. And then adding up all those rectangle areas together gives you the approximation under this curve. Well, I'm going to start from there because that's going from A to B. Okay? So that's how you do a Riemann sum. Now, we can, let's try an example. Let's see if I have an example somewhere. Or maybe not an example, but... Okay, let's talk about trapezoidal. It's nearly the same thing. But this time you're just using trapezoids. So I'm going to draw the same graph. Okay. I'm going from A to B. So like here, right? That looks good enough. So now we're going to use trapezoids. So the trapezoids, you don't have to worry about which side you're doing, because the area of a trapezoid, here, let me write, area of a trapezoid, sorry, I missed the text messages about the prank we did. Area of a trapezoid is 1/2 base 1 plus base 2 times height. Okay, so if I draw my trapezoids here, boom. And these are trapezoids, okay? Yeah, there you go. See that? So trapezoid, how do I flip this? Can I flip my... I can't flip this. Well, whatever. But just pretend we're looking at it sideways. So this would be one base, and this would be the other base. So that's why it doesn't matter, because you're using both y values. You're using the one on the left and the right. You know? The left and the right of this trapezoid. So, so we're just putting this essentially inside of that summation, because we're adding up, we're summing up all the areas of these trapezoids. Do you see that? It's very intuitive. Very intuitive, I swear. And then the height is, again, just the change in x here. You have to pretend like the trapezoid looks like this. It's like on its side. Then it makes sense. This is base 1. This is like base 2. This is the height. Okay, so that's here, height, base 1, base 2. It's hard to write sideways when I'm sitting straight forward. Okay. Oh my god, eraser. Yeah, eraser. Eraser. Let's draw this cleaner. H. So, base 1, base 2. That's our area of trapezoid. Okay, so now let's put that in the summation so we can see what it looks like. So let's do sum here. N, I equaling 1. And then our 1/2 base 1. So I'm going to write y1 plus y2, because these are both y values here. You see that? Y values. The heights. That's what that are. That's what that are. Okay, and then the height, which is the change in x, once again, okay, see, this is like x1, this is x2, you subtract them from each other, and you get the distance, that x, okay? Okay, that's a trapezoidal sum. Trapezoid sum. We're running out of room. Let me move everything over. I'm missing that M. Oh, that's okay. Let's erase this. Let's make it prettier. Pretty. Trapezoid. Trapezoidal sum. Okay, so you see how trapezoidal sum is a much better estimate, because we only have this little bit of space now that we're missing from our estimate. Whereas, oh, I took this off by accident. Whereas over here, we have all this space that we're missing from our estimate. So trapezoidal sum, very nice. Okay. Next. How to integrate. Perhaps? Yes, how to integrate. Okay, these are fundamental theorems of calculus. Fundamental theorem of calculus. Okay, this is so long. I'm gonna move this to be shorter. Oh. There we go. Let's move this right there. Okay, fundamental theorems of calculus. So there's 2. 1. Blah 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 blah. Blah blah blah. What is this telling you? Oh! Okay, so let's say you have a function g of x, and it's equal to the integral from a number to an x. And it's inside you have another function with some variable that's different from x. Well, if you want to take the derivative of this, all you do is you plug in this x into that variable in the function. So simple, very simple. All you do is just plug in the x. So this becomes f of x. That's literally the derivative. Just like that. So easy. So easy. Now, if you had something other than just plain x right there, all you do, you still plug it into here, but then you chain rule it. So if this was like, let's do an example. Let's do an example. I'm just going to leave that there. Let's do an example. So like example. Let's say we had g equaling a to, let's say 1,000 million, whatever, 100,000. Because this number does not matter whatsoever. It's literally just for show. Okay, and then let's say our x was 3x to the 4th. And then we have our function f of t dt. No, let's write an actual thing for our function. X, no, square root. I haven't written one of those. Square root of x squared. No, it has to be a different variable from x. So t squared plus 3 dt. So this variable, this t, these t's, they're dummy variables. They don't do anything. And then they want you to take the derivative. So what do? You take the derivative. And then this does not matter. This goes into the t. So you just write it where the t is. Square root. Okay. 3x to the 4th squared plus 3. Boom. But this is not just plain x, so all you have to do is chain rule it and put that in the behind. So what's the derivative of 3x to the 4th? It's 12x to the 3rd, okay? You multiply 4 down to the 3, there's a 12. And then this 4, you subtract 1, which equals 3. That's what that 3 is. Yes. And that's literally the answer. All you do is plug it in. Just put this right where that t is. It's very simple. That's one of the fundamental theorems of calculus. But you don't need to know that it's called fundamental theorem of calculus. All you have to know is that you can just plug it in. That's your job. You need to know that you can plug it in. Okay, number 2. This is the one that we use to solve integrals. So if we had an integral from a to b of some function f of x dx, then this is equal to the same thing as if you had the antiderivative. Remember, capital F is antiderivative. I don't know if I wrote that up here somewhere. See, capital F, antiderivative. This is integral. Yeah. Capital F, and then remember, you plug in, why is there a ruler? You plug in the b, and then you plug in the a. Okay, so f of b, and then you're subtracting, and then you plug in the a. Okay, so this is literally what we do for all our integrals, our definite integrals, aka the ones with the bounds. Yeah. If you don't have a definite integral, then remember you just have the antiderivative and then you add plus c to the end. Never forget your plus c, because those are worth lots of points. Okay, so let's do example. Let's just go 1 to 3 natural log of x. Very simple. Don't forget your dx. So what is the antiderivative of natural log? That's why I chose natural log, so you can review. Well, the antiderivative of a natural log is 1 over x. No. Natural log of no. What is it? Wait, actually, I don't know. Wait, do we even know this? Antiderivative of natural log of x. X natural log of x minus x. Okay, let's not do this one. I meant to do something more like this. 3x plus 2 dx. And that's because the antiderivative of fractions like this, remember for integral, you have to raise the power by 1 and then divide by the new power. Well, this power is technically x to the negative first, and when you raise it by 1, you get x to 0. And that don't work out. So anyways, you just need to know the derivative, antiderivative of fractions like this with a singular 1 in this degree of x is equal to natural log absolute value of that, what's inside. But you also need a 1/3 out here, and the reason is because if I substituted u sub this equals 3x plus 2, and then du equals 3 dx, and I want to move the 3 to the other side, so I get 1/3 du equals dx. Okay, so this dx becomes 1/3 with the du here. That's what it's replaced with. And then this here just becomes a u, which is very simple to integrate. And remember, when you integrate 1 over u, you get natural log of absolute value of u. So this is u, and here are our absolute value signs. So that is the antiderivative. And then here's your notation with your brackets from 1 to 3. Remember, put them in brackets. And then now we're doing that part where we plug in the b and then we plug in the a into the antiderivative. And this is our antiderivative. So I'm going to remove that bracket so it's cleaner. You only need the bracket on this side, but if you put it on this side, or you could put it here, to be honest. You could put it here so it's cleaner and this is out of the way. But if you put it on this side, you can also, it's easier to see like what you're plugging in. Okay, this is your b value. This is your a value. B goes in here. So 3 times 3 is 9, plus 2 is 1/3 natural log absolute value of 11. But 11 is a positive number, so you don't really need that. Subtract. Now we plug in the a value. 3 times 1 is 3, plus 2. 3 plus 2, 5. 1/3 natural log of 5. And you don't need the absolute value because that is a positive number. And boom, there's your answer. So that's fundamental theorem of calculus. Okay, this is going for way too long, so splitting it up.